Okay, good morning, everyone. So we come to the group lecture. So we are in the fourth lecture today. Lecture 4. So today we'll talk about the Dirac equation. So in the previous lectures, we have learned that the carriers in graphene are massless Dirac fermions, two-dimensional massless Dirac fermions. So why do we call them Dirac fermions, and what do you mean by Dirac fermions? So we will go back to check a little bit about the history of the Dirac equation and how that is related to the research of 2D materials later. Okay, so the important year in quantum mechanics was in around the year of 1925. I would say 1925 to 1926, 28. So that was the time that the Heisenberg and Schrödinger and Dirac, they developed the formulation of quantum mechanics. Okay, so there had been some development before that time, but they don't have a very rigorous mathematical framework at that time. So it was during these 3 years that the modern form of quantum mechanics was developed. Okay, to simplify things a little bit, the whole thing is basically about doing this thing. Is you have a wave function, and then this is equal to the operator of the Hamiltonian applied on it. So you can say the game of quantum mechanics is essentially about guessing the right form of the Hamiltonian. Okay, that is what the game is about. So after you know the form of Hamiltonian, you are going to make a certain substitution that is P go to this, make it an operator, and then you solve the equation, and then you check the eigenvalue of the equation, and then you compare with experiments. So at that time, hydrogen atom is the simplest model, or simplest realistic model at that time that people can have accurate data. So it is an important problem to solve the hydrogen atom and compare that with the emission spectrum of the hydrogen atom, okay, or absorption spectrum. So in the simple case, the classical Hamiltonian, because at that time classical mechanics has developed already, so you should start with something that you know, right? So let's go to the classical Hamiltonian. The classical Hamiltonian usually is pretty simple. It's p squared over 2m. And in the you can apply let me usually we use a v, or sometimes you use v, or sometimes you can use the potential of this, something like that. Okay. Okay. Not t. Okay, not t. So this is the classical Hamiltonian. So and you can write it in terms of energy. Okay. I mean, not Hamiltonian. I mean, it's somewhat similar to the energy. So usually what people do is when you have the E, you make it into this. I just use a simple term. And then you have a P, you make it into this. Okay. Why? Because this E is somewhat correspond to the Hamiltonian, and this Hamiltonian is just this part. Okay. So this is the Hamiltonian, and this you can call it the dispersion. This is the Hamiltonian, and this is the dispersion. They're somewhat related. So if you don't know the Hamiltonian, then you check the dispersion. Then from the dispersion, you make this substitution. Then you get the equation. I mean, the simple case is the Schrodinger equation. Okay, the Schrodinger equation is you have this, and then this one is IH bar square root, okay, 2m, and then VR. Then usually this is the wave function. Then you can copy this and make this negative h bar square. Okay, so that is the Schrodinger equation that you learn in the textbook. Okay. Okay, what is the limitation of the Schrodinger equation? The limitation. Okay, first limitation is it is not compatible with the relativity. Why? Because the Schrodinger equation is not invariant under the Lorentz transformation. I mean, you can already clearly see this derivative on time is first derivative, and this derivative on space is second derivative. I mean, there's no way that after the after the Lorentz transformation you can maintain the same. Okay, because the Lorentz transformation show you the transformation between time and space, right? But here the time is first derivative, the space is second derivative. You can clearly see that if you do the Fourier transform, you're going to mess up the equation. Okay, so that is very obvious that this equation is only good in the non-relativistic limits. The second limitation is that it does not include the spin. Okay, spin is something that probably nobody wanted. And no one invented the concept of spin. It's like not invented out of any like a personal idea, or I should not say personal idea. Not invented out of like any thought experiment, or like spin is something forced by experiment, not the idea that just come purely from theory. Okay, I mean, or you can say the whole theory of quantum mechanics is just forced out by experiments. Okay, people don't really want that or like it, or anyway, because the whole theory is somewhat weird, but the experiment force people to stick to it. Okay, so how do we solve this two issue? Because at that time the existence of spin is already indicated by experiment. When people shoot the electron beam under a magnetic field with a gradient, they see it split into two. When you apply the Zeeman effect, apply the magnetic field, people see the Zeeman splitting. So the existence of a certain internal degree of freedom is already there. But Schrodinger equation does not take care of that. Okay, so this is the limitation. Okay, so how do we take care of it? Then you can see that this equation was guessed or derived, or whatever you want to say, from this dispersion, and this dispersion is non-relativistic. Okay, that's why you don't have a relativistic wave equation. Okay, so let's use a relativistic dispersion. How about we use this one? So this is the dispersion from relativity. Okay, so if you do this same thing here, you do the same substitution, it's negative. Okay, if you do the same thing here, then you're going to get something like this. You're going to get you're going to have the IH bar delta T square, okay? And then this thing, you're going to have a negative C, and then you're going to have this. You're going to have a wave equation like this, okay? So actually, when Schrodinger, before he published his paper on the Schrodinger equation, like what we call the Schrodinger equation, he actually tried this first. And he actually wrote down this equation, okay? But then after you solve this equation for hydrogen atom, you'll find that it does not match the experiment, okay? So since it doesn't match with experiments, then Schrodinger just gave up. Just throw this equation away. I don't know the exact history, but I think it is for a reason to compare with the experiment that he discard this equation. And then we go back to the because at that time special relativity is already well known among the physicists. Okay, I mean the theory was from Einstein's paper was in 1905, and this is 20 years later. Okay, so those theories, they know special relativity, and this dispersion is also known. But they find that if you go from the relativistic equation dispersion, this equation will give you an energy spectrum that does not match the experiment. I mean, now we know why, because electron has the spin, and that changed the results. Okay, and he go back to publish this Schrodinger equation, and it works. If you solve this equation with hydrogen atom, you get the right spectrum. Okay, and this is called the Klein-Gordon equation, because later these two gentlemen, Klein and Gordon, they wrote it, and it turned out that it is a good equation for the spin zero, for the spin zero particles. Okay. For example, Higgs boson is a spin zero particle, and he followed this equation. Okay, so at that time, this issue is still open. That is, what is the correct relativistic equation for electron? Okay, for electron. So this is the problem that they need to solve. The basic idea is this. You go back to this equation. Copy. You go back to this equation. This question is this. What is the so what is the right form of Hamiltonian for an electron? Okay, for an electron. So what is the Hamiltonian for an electron? You cannot just guess from the classical form. Later you'll know, because the classical mechanics does not include the spin. So there's no classical analog of the Hamiltonian for electron. It will be a Hamiltonian that you don't find in the classical mechanics. It's something new. You need to find it. Okay, so then that is the time that the Dirac come into play an important role in the development of quantum mechanics. So Dirac imagined that you have this dispersion. Can you, if you make a square root, then this will be first order. Okay, but somehow this turned out to be very complicated. Okay, so can you come up with the equation of this form? You come up with the equation of this form. Okay, E equal to PC plus M squared. So, I mean, originally, you have E squared equal to P squared C squared M squared E4. Is it possible that you can reduce the dispersion into a form like this? But however, you know that this is a wrong dispersion. Okay, but he imagined that if you add a certain number here, and would it make it happen? So let's imagine you have a certain object. There's another reason why he want a E here, because at that time, if you solve the Klein-Gordon equation, you'll find negative energy value. Because the dispersion allow negative E, because it's square. So even negative E will give you the right dispersion. Okay, so if you include the square in the delta T, you'll find that you solve the equation, you have negative energy. Okay, and at that time, people have not discovered any data that shows negative energy. So Dirac knows that negative energy is what he does not want. And that root comes from this second derivative. So he only wants a E in one side. But since E is on one side, then on the other side, you need to get rid of this square. Okay, so he just imagines there is E with a certain number, which you need to get, and then show a dispersion like this. He wants a form of the dispersion like this, or you can say he wants a Hamiltonian with a form like this. Okay, it's a game of guessing. Okay, so you need to use your imagination. So suppose you have two numbers here, gamma and beta, and then you take a square. Okay, you take a square. Then you will have square PC and beta, and then you have this. Let me see. PC MC squared. Okay. Okay, this will be possible if sorry, square. Okay, square. If this is 0 and this is 0, and then sorry, this is 1. Okay, if you can find a number that satisfies, or you can find beta and alpha that satisfy this dispersion, then you will make it work. Okay, but you know that this will never work if you just simply use the number. There's no ordinary number that can satisfy this. I mean, you can already see that this will give you, if it is an ordinary number, then this one will give you alpha equal to +1 or -1, beta equal to +1 or -1. But then this one will give you this or alpha equal to 0. You never get a solution. Okay. So normal people will just stop here. It doesn't work. But the Dirac is a genius. He move on. He find that if this is not ordinary number, if they're matrix, then you'll make it work. Okay, you'll make it work. So let's consider a 1D case. Let's consider alpha equal to this. This is basically a Pauli matrix, sigma x, okay? And beta equal to this. This is a sigma z, Pauli matrix, okay? Matrices. If you use matrix instead of number, you will make it work, okay? So in this case, the matrices at least need to be 2 by 2, okay? Because 1 is just an ordinary number, then you go one step further, it will be 2 by 2, okay? So you can actually confirm it, because square, you take a square, you get 1. The same for beta. You can easily confirm that this will be 1. Okay, you can call it 1. 2 by 2. Okay, and you can also confirm that alpha beta plus beta alpha will be 0. Let's quickly do it then. It's pretty straightforward. Plus. Okay, then what is this? This is 1. This will be 0, 1, and then -1, 0. Okay. This will be, let me see, 0, -1, 1, 0. So you get 0. So if you put this matrix into this, into this let me see, into this, then from there you get a Hamiltonian that is 0, 1, 1, 0 PC plus 1, -1. So this is the Hamiltonian. This is the Hamiltonian for 1D electron. For 1D electron. Why is it 1D? Because you only have a P here. If you have a PX, PY, PZ, then you need more matrices. And later we'll deal with it. Okay. Then you continue to do the substitution. So I H bar delta T, the wave function will be H bar, right? Will be not H bar, H Hamiltonian. Okay, then you just substitute it. Then this will be an operator. Okay. 1, 0, 0, -1. Okay, basically here it automatically means your wave function must have 2 components. Otherwise, the matrix will not be meaningful. Okay, so your wave function need to at least have 2 components. Okay, then you then you just make this a 2-component wave function. Let's say 1, 2. Here we only deal with 1D. Deal with 1D. So this is just x, and this P will be just PX. This P will be just a PX. Okay, just a PX. Okay, so this will be X, XT, XT. Then PX will become DX. Okay, so I think I missed a negative sign here. I think this should be a negative sign. h bar over I. Either way is fine. It should be a negative sign. Okay, you have a negative sign. Then the wave function will become like this. And then you have a h bar over I. The speed of light is here. Then you have dx. Amps, you have mc square. Okay, so this is the 1D Dirac equation. This is the 1D. This is the 1D Dirac equation. So this equation is good for describing like a carbon nanotube. Okay, let's say in carbon nanotube. Of course, not all the carbon nanotubes, but I think some, because for carbon nanotube you have a dispersion like this. When the mass is 0, or you open a gap. But they are all 1D systems. Okay, I'm not sure whether it's applicable for all carbon nanotubes, but some. Okay, basically whenever you see a linear dispersion, then it will be this Dirac equation. For 1D, then it's 1D. When there's a gap, then there's a Dirac equation, open the gap. Okay. Okay. So this is the 1D Dirac equation. The 1D Dirac equation. You can write it in a better form. Let me see. You can write in a better form. So if you want to write in a better form, then you just use the sigma, sigma x pc. This is sigma z m square, sigma z. Okay. Then of course this is x. Okay. So you can change this into the differentiation. Then you get what I got here. Okay. Okay. So this is the Hamiltonian. This is the Hamiltonian of a 1D electron. Okay. The spin is already included. The spin is already here. I'm not sure whether I can say this is the spin because it's a 1D system. Okay. Okay, let's go to 2D. Let's go to 2D. Okay. If you go to 2D, then you have a px. Okay. Because here you can see that the original dispersion is square. Is square. So when p is a vector, then it will be a vector square. Okay. So that means p need to be a vector. This is magnitude certainly, but in 2D, then the momentum is a vector, right? Okay. So that means here this p need to have two components. This p need to show the two components because it's a dispersion in 2D, right? So dispersion is energy as a function of momentum, right? And the momentum is a 2D vector. So this energy need to be expressed in terms of the x component and y components. Okay. So the dispersion for 2D electron then the dispersion will need, you need to come up with let's say alpha 1 or and alpha 2, this is x, and py c. Okay, so this will be the form that you want. Okay, then let's square it. Okay, if you square it, then you'll get a lot of terms. Let me just write all of them out then. It's not that much, it's not that many. Okay, so you'll get this px square, and then you have py square, and then you have beta square. Okay, then you're going to have different combination. Px py, and then plus px c mc square, and then this py c mc square. Okay, so in order to make it recover, you want this to go to 0. You want it to go to 0. You want this to be 0, and you want this to be 1. You want that to happen, so that you can go back to the original one. Okay, so if this happen, then you have px py, and then m4. You go back to the original dispersion. Okay, so then you need to find some matrices to make this happen, and the answer is also very simple. You can still use the Pauli matrices. You set this to be this, and then you use sigma I, and then beta you still use sigma z. Then you can readily confirm that for Pauli matrices, sigma I square will equal to 1. Okay, I is x, y, z. Okay, and then if you use this, this means that this, okay, anti-commutator, it will be 0. That is the property of the let me see, this is will be, let me see, let me write it here, will be 0 if I doesn't equal to j. And then it will be, let me see, it will be 2 if I equal to j. Okay, so this is the anti-commutation. Okay, so the Hamiltonian will have a form like this: pxc y py c. So still, this kind of Hamiltonian you cannot find in any classical mechanics. So it is there because electron is not a classical object because it has the spin. Okay. Then you just substitute. Then eventually you substitute it. Then of course this one will be in terms of x, y, and t, and x, y, and t. Okay. So then you will have h I, C, and then it will be 1, 1, 0. And then this one will be you can actually group this together. Group this together. Px will be delta x, and then you have a y component, delta y. So it will be 1 and 2, and then you also have this. Let me make it somewhat smaller. Okay. And then you have a mc square, 1, 1, -1. Okay. So eventually, you will have a form like this: x minus y, and let me see. Huh? Sorry, it's 0 here. Okay. Anyway, okay. So let me check. Okay. Okay. So okay. So you get the equation like that, then you can already see that it is the form of the Hamiltonian that you see in graphene. Okay. If m is 0, then you get a 2D massless Dirac equation. So these are, if you solve the dispersion, you will see a dispersion like this. M is equal to 0. Okay. Okay. I mean, the slope here will be C. This will be the slope here will be E equal to PC. Okay. If you plot as a function of if mass is 0, then you will see a cone. Okay. It's 2D, so it will be a cone. So if you plot as a function of this k, like, then this slope, the slope is C. Okay, in graphene is the Fermi velocity, but it has the same form. So if m is not equal to 0, then you will have a gap. Okay, a gap. If m is not equal to 0, then you open a gap. Okay, you open a gap. Right. You open a gap. Okay. And this gap size, with this part is plus MC, and this part is minus MC. So the total gap size is 2MC squared. Okay. So eventually this M will be related to the curvature of the band. Okay. And the whole band gap will be will be 2mc squared. Okay. This will be the case for MOS2 or TMD material. They follow a 2D massive Dirac equation. So they open the gap. Okay. And graphene is just when the mass is 0. Okay, so this is why we call the electrons in graphene the massless 2D Dirac fermion. Because they follow this 2D Dirac equation. Is it okay?
I am if we consider the free electron in the solid, then what is the meaning of the negative charge?
Sorry, what's the question?
I want to know the meaning of negative charge for free electron.
Meaning of negative for free electron. That is you just go to the energy of the hole. Yeah. Yeah. You take the reference in the middle of the band gap at 0, then the energy of the hole in the valence band, that is the energy. Because negative energy, you need to have a reference. Yeah. Sorry, I'm charging my my Apple Pencil. So let's talk a little bit.
For the band structure, then we also very quickly then I can consider it as a port, because if that electron is just free and there's no lattice, then
you mean just a free electron in vacuum?
Yes.
Then the negative energy, those are the positron. Those are the antiparticle. If you can shoot a photon, I think in this case you need 2 photons, okay, because of this angular momentum conservation. If you shoot a photon or 2 photons with enough energy to match the gap, you will excite an electron and positron pair. But of course, the energy is about 1 mega eV. 1 mega eV. Those are in the gamma ray range. So if you have a strong enough gamma ray, usually I think you need 2 for the angular momentum conservation. Then you in principle you can generate an electron positron pair. I mean this people have observed this because when Dirac first published the equation, then this negative energy stays there, and at that time nobody have ever observed such particle with negative energy. So Dirac actually come up with an explanation. He originally thought that that might corresponding to proton, because proton has positive charge, but it doesn't really match. Then he actually used he actually thought that the whole world is filled in a electron sea that fill the negative band. Like all of them are filled, like the valence band that are filled with electrons. But because it's filled everywhere and fill the whole world, so all the effect cancel out. We just don't feel them. And then when you shine the light, you can excite. But you can never neglect those states, because when you shine the light, you can excite an electron in the negative band to the higher band. So in principle, you will have such a transition, even if it's filled. So you need to resolve the question of there's a band. Then when you have an electron, then you will relax all the way down, and there's no bottom, because we know particles tend to relax, right? Then when there's a band with a negative energy all the way to infinity, then the electron cannot stay there. They will relax and just keep relaxing and just keep going. And this doesn't make sense. So he just imagined that the lower band need to be filled so that this electron gets stuck there. Because by Pauli exclusion principle, it cannot relax anymore. So this resolves one concern. Okay. The second concern is that there will be transition, because you have electron here, you have a transition to go up. But this transition has never been observed. But of course, the energy is very large. But after a few years, in I think it's around the time of 1932, then people observed the positron. At that time, there's no accelerator. They just use the gamma ray from the cosmos. cosmos ray, cosmic ray. Okay, I mean now you can see in your CCD the cosmic ray even in this room. In your CCD, sometimes when you measure, you see a spike, right? Those are the cosmic ray, the gamma photon hitting a CCD and generate a strong signal. They're everywhere. So they build a cloud chamber, with an oversaturated gas. So when the high energy particle goes through, they will leave a trace, and then they apply magnetic field from the curving of the particle. Then you can deduce the charge and also the mass and those information. So basically, at that time, they just build a cloud chamber and just wait. Just watch and then they see the trace, and then they get, oh, there's a particle with a certain mass but opposite charge with the electron. Then they discover the positron. Okay, that is the story. That antiparticle was actually first anticipated by theory. It's a very few quantum mechanical results are the theory goes first. Usually the experiment, see it, the theory follows, but not many of them are. Of course, now in condensed matter, people are predicting all kinds of stuff, but in the fundamental level, not many of them are first predicted and later see. But and antiparticle was one novel example, very fancy example that he actually come by theory first. Okay. Okay, I guess we can continue. Okay. Okay, 1 hour. Okay, so let's continue. Okay, so now we come to a very non-trivial extension to 3D. If you want to extend it to 3D, that is, then you have this PXC, PYC, and PZC, and then you have beta. Okay, so if you go to 3D, Dirac equation. If you go to 3D, you'll find that you already use up all your Pauli matrices, because you already have sigma, you use Y, you use Z. Then what else? What is left in the 2x2 matrix is just one by one. So because for all 2x2 matrices, let's say A, 2x2, they can all expand into a linear combination of AY, AZ, and I don't know what this is called. Let me just use a number then. It's easier. A1, A2, A3. Sorry, 2x2. So for all 2x2 matrices, you can always express them as a linear combination of this sigma X, sigma Y, sigma Z, and the identity matrix. But that's all. Okay, but the problem is this identity matrix, it commutes with all the other matrices. You cannot use it because because you want a relationship like this. You want a relationship that all of them multiplied by themselves is 1, and then they follow this anti-commutation. Okay. However, for the identity matrix, you cannot fulfill this. Okay. You will not get 0 with the other. But in the 2D case, you already use sigma X, sigma Y, sigma Z. You already use all of them. So there's no more. Okay. So how do you deal with the 3D case? But our world is a 3D. You have electrons in 3D space. So what should we do? then you have to go to a higher dimension matrix. So the lowest dimension of matrices is 4 by 4. It's 4 by 4. Okay. So so let me quickly write the answer. Okay. So in this case, the matrices Dirac find is this is X. This is the matrices that he find. Basically this. Okay. And then this will be basically you take the Pauli matrices and put them in the off diagonal place position. Then okay, so and then this will be sigma z. 1, -1, 1, -1. And then beta, beta will be sigma z. Beta will be the I or I and -I. Basically is 1, 1, -1, -1. Okay, so you can define a vector of matrix as 1 x 2 y. I mean, it's not a real space vector. It's just for convenience, you define it in this way. Okay, then the Hamiltonian will be sigma 1 pxc. Not sigma, it's alpha. Alpha 2 pyc, alpha 3 pzc, and then beta mc squared. Or using a matrix form, you can write it in this way. Okay, so this will be the Hamiltonian for 3D electron. Then naturally means your wave function need to have 4 components. Okay, need to have 4 components. So the wave function, you will have, you can write it in this way. Let me see. You can we actually write it in this way. And here I use a different name. Use a chi 1 or chi 2. Okay, so basically, in order to accurately represent the electron, the wave function need to have 4 components. If you solve the equation for a free electron in 2D, like with no any potential, so for free electron, this two will be electron with positive energy, and this will be a positron with negative energy. This will be positron. This will be exciton. Sorry, electron. If you solve it. However, if you have a potential, you can have a linear combination of electron and positron. Like because electron and positron, they are essentially they're described by the same wave function. Okay, so they can actually have a linear combination. So the general wave function of the electron will have the electron component and positron component. But of course, in order to couple them together, your potential need to be very big. like comparable to the band gap. And usually it's quite difficult to find the potential that big. So usually electron and positron can be treated separately. Okay. 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 Any questions? Any questions? Of course, because of this 4 components, solving the 3D Dirac equation is not easy. But for free electrons is solvable. You solve it, you see a 3D Dirac cone and you can open the gap. Okay. And this equation is the basis for the field theory of electron in high energy. Yeah. So if you learn high energy, you have to learn this high energy physics. You have to learn this 3D Dirac equation. Okay. Any questions before we move on? So let me make a short summary what we have been doing. Then we go to the next section, so okay. So far, I go through how the Dirac equation was found. Okay, basically it was the game of finding the right Hamiltonian for your system, and usually people can start with the classical Hamiltonian, and then you can find the Schrodinger equation in this way. Basically, you can say it is a guess using your physical intuition, and then you solve it to get the eigen energy and compare with the experiment. If you match, then the equation is the right one. That is how the theory works. It's not like a logic like those logic in mathematics. You need some intuition to guess. Okay, guess and then compare with the experiment. Okay, so but for electron, it turned out that the Hamiltonian has no classical analog. It is something like completely new, and you have to incorporate this matrix into it in order to get the right result. And it turned out that in 3D case, in 1D and 2D case, you can use 2x2 matrices. So that's why for 2D direct fermion, the wave function is only 2 components. Okay, but once you go to 3D, then you have to go to 4x4. Okay, 4x4, and the spin and the antiparticle just come out directly due to this method. You have because this one later you see that these are the spinner of the electron, spin up, spin down, and this is the spin up, spin down state for the positron. So these 4 components include the spin up and down and the electrons and positron. So you can see that the spin is actually a result of relativity. Why? Because of relativity, you need a new Hamiltonian. Okay, that is compatible with relativity. Because of relativity, the space and time need to be treated equally. When you have first derivative on time, you also need to have first derivative on space. So that's why you have a Hamiltonian of this form. Okay, it is linear in P. Okay, once it is linear in P, you have to use the matrices. Once you use the matrices, then the spin and the antiparticle just come out. So the existence of spin and an antiparticle, they are due to the requirement of consistency with the special relativity. So you, in another word, you can say the spin and antiparticle are kind of a signature of relativity. So relativity has the effect even if the particle is not traveling at the speed of light or close to the speed of light. Even when the particle stays there, not moving at all, it will still have the relativity effect. The spin it comes from that, and antiparticle comes from that. So relativity doesn't mean you have to move very fast. Even when it doesn't move at all, it will still have the signature there. Okay. Light, of course, have spin. You spin up and one and negative one. Yeah, we talk about spin zero equation, spin zero particle equation, the Klein-Gordon, and this is spin half particle equation. If you go to spin one, then it will be the Maxwell equation. You quantize it, then you get the equation for photon. Okay. Okay, now let's take the relativistic limit of the Dirac equation. Then the G factor of the electron will come out, and it turned out to be very different from the classical case. Okay, so let's take the Dirac the non-relativistic of the non-relative, take the non-relativistic limit of the 3D Dirac equation. Okay, so let me see. So let's consider in the presence of EM field. So how do we take care of the EM field? It's actually very simple. So the electric field is the gradient of this potential, and then the time derivative of this magnetic potential. Okay, and the B field is this. Okay, so basically you need to incorporate this into the equation. How do we do it? So originally, so let me use this big let me write it better. This big thing. Let me use this. Okay, bigger one. Okay, so you use a bigger one, and this will be so you know this is a 4x4, right? Okay, so with this one, with the EM field, it will become something like this. You by this substitution, you change this P, you change this into, you still have the dot here, and then you minus ECA. Okay, and then here here you add the potential. You have a charge here, so like this. Okay, so this is the potential. Okay, so this is because in the previous cases, like in the Schrodinger equation case, that is how we deal with the potential. You take the P and then include this one, and then you add the potential. So if you take care of the EM field in the Schrodinger equation, this is what you do. Okay, and I think you learned this in the textbook, right? You just use the same strategy for the Dirac equation, same substitution. How do we justify that this is the right way? I don't think there's any like I mean, I don't know any mathematical justification. I think the best justification is that you do it this way, you solve the equation and you compare with the experiment and it just works. Okay, and that is how we do it. Okay, that according to what I know. I don't know any deeper philosophy why you do it this way, because quantum mechanics is half logic and half intuition and trying, and you solve it, you get the right answer and compare with the experiment, and that is the right one. So it's not like completely just mathematical logic. It includes some intuition and trying there. Okay. And we call this pi. Okay, pi vector. Okay. So we want to take the non-relativistic limit. So we are going to represent this by this. So in the non-relativistic case, case of electron, because we're only interested in electron, we're not dealing with positron. So is dominates, and chi is small. Why? Because chi is a positron. The chi part is positron, and this phi part is electron. So you expect this will be big and this will be small. So if something is small, then you can expand them out and then only focus on the electron side. But this expansion on the small part will give you will give you the result, and we'll show you some non-trivial properties. Okay, so let's rewrite the equation. The equation will be T, and then it will be each of these are 2 by 2, a 2 component wave function. Okay, each of them are 2 component wave function. So the pi is here, and this is the dot, and then this will be this. Okay, and then this will be 1, -1 MC. And then plus the potential. Oh yeah. Okay. This means is sigma x, sigma y, sigma z. You make them into a vector, so that I mean they're not any real space vector. It's just a convenient convention to write the equation using a dot product. Okay, so this one equal to just a convention, and then you can expand it out. Then you will have something like that. T chi negative MC. Okay. This is equation 1. This is equation 2. So we know that in our consideration, chi will be small. Okay. So we're going to use this property. Okay. So equation 2 can be written as, okay, so this equation 2, let me copy. We're going to deal with this equation first. Let me see. So you are going to so we're going to add the 2 MC squared chi on one side and add another 2 MC squared chi on the other side. Okay, then you have 2 MC squared chi and MC, and then this will be negative T, and then this will become plus. I mean, these two combine, then we'll give this And then you will just okay. 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 Then you you just divide it, and then I want to move the negative side out, so everything inside just become like this. Okay. And then of course you can cancel this C. So you have only one C. So you cancel this C. So you only have one C in the bottom. I only have one C. Okay. So why do we do it in this way? Because now you're expressing this chi in terms of phi. And you can see that it is 1 over C. And C is a big number, right? So this already shows that chi is small. And this order is 1 over C squared, is even smaller. Okay. So if this chi is originally small, then this basically is a good representation. Then you only take the leading term, then this will give you quite a good approximation. Okay. But of course, if chi is big, then it's another story. But if you know that chi is small, then this will give you a way to do expansion. Okay. Okay, so the major term is this one. The major term is this one. So here you can do iteration. That means you put this whole thing back to here. You keep doing this, then you're going to have a iteration. Okay, but you know that if you do iteration, we can do iteration. On chi. The major term, the leading term. The terms are okay. So if you only do it like this, then this will be the leading term. Okay, the leading term will be and then if you do it more, then like then you just take this and then put this here. Okay, so this will be another iteration. So like one iteration, like one iteration, you have it like this. Okay, so this is an expression of chi in terms of phi, and to the order of 1 over C squared. So what that is all we are going to do. We will only cut it up to 1 over C squared. Okay, if you have 1 over C cubed, and then we don't consider those higher terms. Okay, then then we go to equation 1. Copy. Okay. And let's say this is equation 3. Yeah. Equation P3. Then you just put equation 3 into equation 1. Then what you're going to get is Let me see where you're going to get. So, yeah. Okay, you I just write the result then. Okay, I just write the result. If you put it, you have a term like this, and then you have MC squared plus. Okay, this is just this term. Okay. So what is this term? This term is you take this, and then you combine with this, then you get this term. Okay. Okay. Then later, you're going to have this term. Okay. This term times this. Okay. So you're going to have this thing combined with this. Okay. You have a MC here, and 2MC squared here. Okay. So, and you have a C here. So eventually, you will get 4M squared C squared I, and then you have I H bar T minus MC minus, yeah, sorry, I think I need to make it smaller. Okay, make it smaller. Okay, so this is the equation, and this is term 1. 1. This is term 2. Okay, so we're going to deal with them one by one. I think in today's lecture, I will only deal with term 1, and this will give us the Zeeman effect and the G factor of electron. And if you deal with term 2, you're going to have the spin-orbit coupling that will pop out. Okay, and let's deal with term 1. Okay, so let's deal with this term. After finish this term, I think we'll know why the Zeeman effect will come out. Okay, for term 1, so term 1. So this one is equal to 2M okay, so how do we solve this? We are going to use this equation. Okay, so A and B are vector. Okay, and the sigma are matrices. Okay, is a vector of matrices, Pauli matrices. So what is this? This is basically you have a dot product, AI, sigma I, and then you have BJ, sigma J. These are just the product, the dot product. And then let me see. You can move the A and B on one side, the sigma IJ on the other side, and then you can separate this into 2. That is when the I equal to J. If they're equal to J, then this IJ will be just 1. Okay. But this one will be I not equal to j. So if I is not equal to j, you can check the property of Pauli matrices. I mean, you can just get this result that this will be I, K, and epsilon ijk. Okay, I hope you understand the meaning of epsilon. So K will be the third matrix. Like if you have ij as x and y, then K will be z. If you have ij is x and z, then K will be y. Okay, so then this thing, this whole thing will be 1, right? So once it is 1, then this one it's just ai bi, and you just sum over I because they're equal, right? Okay, and this will be, this I is a complex number. Okay, imaginary number. This will be sigma k will be I not equal to j sum over. So this will be epsilon ijk this. Okay, so you can actually change this into, you can actually anyway, you once you use this, you don't need that because when I and j are 0, this one will automatically be 0. Like this symbol already take care of the not equal. Okay, it already take care of the not equal. So you can move the k here to the beginning, and then I and j, like you rotate it. Okay, then what is this? This is this is the cross product. Sorry, I make mistake. This is a and b. Sorry, this is a and b. This sigma k is here. Okay. This is a and b. Okay, so this is just a cross b. A cross b and the k component. Okay, the k component. So this whole thing here, just a dot b. This is delta k, sigma k, and this is a cross b k component, and you need to sum them together, right? Let me see. Then you have I sigma dot a cross b. And here you automatically need to sum over k. Yeah, because as you're going through I, j, and k, you basically automatically you need to go through k again. Let me see. Like here, you I'm using this. As you go through, I don't know how to represent it correctly. It's because as you go through all this summation, your k is automatically also going through it. Okay, so here you actually need to go through different k and sum them together. So it will be actually a dot product. Actually, in my notes, I didn't write this thing in the notes. I just used the Einstein summation. I just write it in this way. So overall, you need to sum over ijk, ijk. Yeah, so I think here basically you need to sum over IJK. Okay. The I not equal to JK is already taken care by this symbol, because when they're equal, this symbol will be 0. Okay. Yeah, so that is the equation. Okay, so we're going to use this result because this is the form that we use. So you're going to have 2m. You're going to have pi square plus I sigma dot pi cross pi. You just use this equation. Then you, because in this case both A and B are pi. So you have A cross B is pi cross pi. But you need to know that pi cross pi is not 0. Pi cross pi is not 0. Later I'll show you. It's not 0. So what is pi cross pi? So let's consider. Pi cross pi is this. You have because this is P, because P is an operator, okay? Because P and A are not, they don't commute. So they won't be 0. So when you deal with operators with this cross product, you need to be careful because they're not commute. So you cannot just apply a normal vector property on it. You should just deal with this step by step. Okay. So I think a more careful way to deal with it is just to use the derivative. So this, and then this will be the sorry, this is minus. And then this will be E over CA. E over CA. And then you expand it. You expand it, you just bring all the constant out. So this one, cross product, this will be 0. This will be 0. Okay. And this one, cross product, this one will also be 0 because they commute. Once they commute and they cross, then it's 0. Okay. I mean, you can prove it easily. Okay. I just use the cross product. So the only term that will give you the trouble is this one, cross A. This one, cross A. And then plus A cross this. Like this one cross this. Sorry, this one cross this will give you this. And this one cross this will give you this. Okay. So they are all operators. So what does it mean? This one means you have a wave function, you multiply on A first, and then do the curl on the product. This one means you do the gradient first and then cross product with A. Okay. So let's deal with this part. Let's deal with this part. Okay, so this one, what is this? This is IJK and J and K. And this one is IJK and AJ and K. Okay. So what does it mean? This one, you need to know if you have this on the wave function, what does it mean? It means you deal with this part first and then do the derivative later. Okay. So then you have a product rule. Okay. So you have this. Okay, you have this. Is it okay? So you will deal with this. This will be This will be AK. And then IJK, this will be let me see. You have let me see. You can take away the wave function, okay? Because that is the operation, okay? And then AK. Wait. No. Sorry. I write this term first. Okay, this term is JAK. Use a parenthesis. And then I write the second term first. This term will be just AK with this. Okay, with this. Because the operator is just this part. So I just write it here. Okay. Here, the operator is just a multiplication of a function. So it's this part. Because we are writing the operator. So I don't want to have the wave function inside. Okay. So basically this operation equal to this thing. Due to the product rule. Okay, you can verify. And then you can write this here. Okay. Let me move up a little bit. Make it slightly smaller. Okay, so you'll find that this thing is 0. Why? Because they are opposite. Okay, so this is KJ, this is JK. They have the identical, the same form, but they switch the index. Okay, so if you want to know why, then you can just rename it IJK. And then because here JK are dummy variables, the dummy variables. Okay, so you can change interchange J and K, the dummy variables. Then this will be K, this will be J. Okay, then you have IJK sum over KJ and AK, and this thing is 0 because they're negative of each other. Okay, so it's 0. Let me someone make it smaller. Okay. Okay, so that means this thing is equal to IJK. Okay, so what is this? This is just the curl of A and the I component. Okay, so the curl of A is just the B. It's just the B field. The B field I component. Is okay? So this whole thing is just EHC, HI, and the B field. Yeah, that's it. Okay, so the result turned out to be very simple. Okay, so this whole thing is just pi squared 2m. Then you bring this inside. You bring this inside. you have an I here. Okay, you have this part. Then you just put it here. Then you'll reach a result of this. 2mc sigma dot p. Is it okay? And this is the Zeeman effect. Okay. And this thing is the Zeeman effect. Okay. So basically, Zeeman effect is inside this term. Include the Zeeman term. Because we are dealing with term 1, and term 1 has this one, and this is Zeeman. You can see that this is the sigma dot B. So that is the spin dot product with the magnetic field. Okay, so that is the spin Zeeman. Is it okay? Yeah, is it okay? Okay, so from there we can get the G factor of the electron. The G factor of the electron. I mean, we are almost done. We deal with the G factor, then we're done. Okay, so let's okay, G factor of electron. So this Zeeman term is this. Okay, this is what we derive from the Dirac equation. So let's go back to define magnetic moment. Magnetic moment is defined, defined as mu equal to 1/2 R cross J. J is the current density. Okay. The factor 2 is by convention. So that for a closed loop of current, if you have a closed loop of current like this, I, then the magnetic moment will be 1/2. You need to sum over the this whole area. Okay, if you sum over this whole area, then by using this I think, is it the Stokes theorem? Okay, then it will be the integration over this current, over it, and then you'll find that this one will just give you 2 times of the area. 2 times of the area. Like let me see. Area 8. So this thing will give you 2 times of the area. And eventually this 1/2 is used to cancel the 2 times. And then you have the current times the A. So I think I mean, I don't know the history very well on this part. I think historically people define the magnetic moment in this way. You have a closed loop, and current and area are very easy to measure, right? They just make a product and just define it as magnetic moment. But if you take this as the definition, then when you go to the microscopic level of a current density, you have to add the 1/2 to make them consistent. Okay, that's just a historical reason. I think. I mean, I did check the history carefully, but it makes sense, right? Okay. Okay, so now let's consider for a point particle. For a point particle, what is the mu? Then you just go back to the same definition. Let's say the Q is the charge. with charge Q. Then here, this current density is simply J is simply just Q times V. Of course, it should be a delta function. It will be a Q times V with a delta function because it's a point particle. Okay, so you need to integrate over. So the mu will be have this form. Okay, for a point particle. Then you can express it in terms of angular momentum. So the way you do it is multiply mass. A mass. You have a R cross a mass V. So this is basically R cross P, right? So then you have Q to M angular momentum. Okay, yep. So that means for a point particle, if you know the angular momentum, you use this equation, you get mu for a classical particle. So historically, Bohr's postulate you can say Bohr postulate that the minimum angular momentum is L equal to h bar. Okay, so that means the magnetic moment will have a minimum value. So the quanta of magnetic moment. Yeah. I always sometimes I accidentally hit the arrow. Moment is mu b. Mu b equal to Q2 h bar. Okay. Then is for electron, it will be this. For electron. So this is called the Bohr magneton. The Bohr magneton. So Bohr magneton is just a result of the quantization of angular momentum. You just put h bar there. Okay. So the energy of this magnetic dipole under B field under B field is this this form. You have a mu dot B. That's it. Okay, so what is a mu? In this case, is E2M and then L dot B. Okay, so this is the energy. So for a spin half particle, let's say electron. Okay, the angular momentum is one half of h bar. Okay, so I mean you can okay, one half of h bar. Of course, you should add the sigma to make it an operator. Okay, you add the sigma to add the operator. So the Hamiltonian, here once you make it operator, then it's no longer electron, it's a Hamiltonian. Okay, the Hamiltonian will be negative 2m, and then you have a h bar over 2. You make it a sigma, and then dot B. Okay, you compare this with the Zeeman term. What is the Zeeman term? Let's go back and check the Zeeman term. Okay, so this is the Zeeman term you obtain from Dirac equation. So you compare them. It is only 1/2 of the value. So why? Let me see. You have 1/2 here. You just compare. You already see, right? There's a 1/2 here. Okay, so that means this Hamiltonian is wrong. So the correct Hamiltonian is this one. But you use the classical consideration, you miss a factor of 2. Okay, so how do we fix it? I mean, this one is from Dirac equation is the correct one, and experimentally is also correct. When you do the experiment, it followed this Zeeman shift predicted by the Dirac equation, not this. So the classical case is wrong. Okay, but of course we people get used to the classical result. Okay, if you still want to use the classical result, you have to put the factor there to correct it. So that correction factor is the G factor. G factor is a way to save the classical model. This what was it is just an artificial factor that put there to make it work. Okay. So people gives a G factor to fix it. So the Hamiltonian will be negative G factor, and then this will be the Bohr, because we use the Bohr magneton. Okay. Okay, so you use the Bohr magneton, and G will be 2 for electron. Okay, so that is how the G factor of 2. So G factor of 2 is a result of relativity. Okay. I knew a friend when he was a graduate student. He's a theorist, so he wanted to find an advisor. So when he talked to his advisor, his advisor kind of want to test his knowledge of physics. He asked him, in condensed matter, is there any relativistic effects that we need to consider? Then he said, yes, spin orbit coupling. Yeah, the G factor of 2. Because this G factor of 2 is the for spin. The G factor of 2 is the relativistic effect. So so things related to magnetic property, related to spin, they're closely related to relativity, because the B field is 1/c derivative of E. If the C is infinite, there's no magnetic field. Okay, so magnetic field itself is already a relativistic effect. The spin is also, I mean, the existence of spin is because of this consistency with the relativity. So this G factor is also due to, I mean, the Dirac equation due to the consistency with the relativity. So spin overall is a very interesting object. So this factor of 2, you see in other property. For example, you rotate a spin by 1 round, it becomes negative. You rotate it by 2 rounds, then it becomes itself. You have a 2 there. The angular momentum is 1/2. You have a 2 there. Then here you also have a G factor of 2. So spin overall has this like an interesting property associated with the number 2, or 1/2. Okay. So let me oh, we are almost done. Okay. So the mass is important for the magnetic moment. Let me give you an example. Because the magnetic moment has has an M here. Why do we have an M? I mean, initially you don't have an M because you want to make angular momentum appear. You add the M and then divide the M. But then once this thing becomes the angular momentum, the quantization does not depend on M. For all particles, the angular momentum is all have a quantization value of h bar. Then it turned out that the minimum, the quanta of the magnetic moment, it turned out to be related to 1 over M. So that means the heavier it is, the smaller the magnetic moment will be. So for example, for electron, the mu is negative EH bar ME sigma. For proton, let's say this is E, then it is P. It will be, let me see, wait, let me just write the result. I want to include the G factor. Will be the G factor of the electron. Yeah, I just write the result then. Okay. So here it will be the G factor of proton and EH because it's positive. Okay. So it's proton. Okay. So the proton magnetic moment will have two things that are different from electron. First, the mass is much heavier, so it's small. Another thing is actually the proton has a different G factor. Because proton is not one particle, there are 3 quarks inside, and the quarks are interacting. So each quark follow the Dirac equation, and it will have a G factor of 2. But when these 3 quarks combine together and interact, then somehow the overall G factor will be different. Okay. So is of course the details I don't know, but you just need to know the G factor for proton and neutron are not the same. And because the quarks inside, although their charge can cancel, their magnetic property cannot cancel. So that's why in neutron, the quarks inside, the 3 quarks inside, the charges cancel, but their magnetic moment they don't cancel. So the neutron has 0 charge, but it has a finite magnetic moment. There's some because it's not one particle, it's 3 particles interacting inside. Okay, so the neutron has no charge and magnetic moment. So it turned out to be very useful to do some diffraction that are related to magnetic order, because they don't interact with the charge, only interact with the magnetic moment. So you can use neutron to do diffraction to detect the magnetic order. For example, if you have a spin liquid, you want to see whether there's an order inside, then people do neutron scattering, and they don't see any order, then they use that as support for the spin liquid state. Okay, these are like some more information. Okay, so finally, let me give you an example why this G factor of 2 is related to us. Like why do we need to care them? Okay, I mean we do all this thing on Dirac equation, all of this, and we get a G factor of 2. How is that related to our research? We deal with G factor of 2 in our research. For example, for WSE2, let's say monolayer, then you have 2 bands. You have 2 bands and 2 valleys. We know this. So this is spin up, and spin down. This is opposite. So spin up, spin down, and spin down. Okay. So this the conduction band has M equal to 0. Okay. So this one, I think it has M of let's say +2 then. And this one is -2. I don't know which one is +2 and -2, but one of them. Okay. Because the 2 values are related to time reversal symmetry. So once you apply the magnetic field, what will happen? If this is B equal to 0. Okay. If you have be not equal to 0. So how are you going to change it? Let me copy them. Okay. So that this thing is going to move up. Okay, move up. Okay. By the way, this 2 is already the, like, you move up by a unit of 2. Okay. Because m means I mean, this means that the angular momentum is 2h bar. Okay, so 1h bar will give you a ball magneton, right? So 2h bar will give you 2 ball magnetons. So you shift up by 2. Okay, by unit of 2. And a unit of 1 means the shift of 1 ball magneton. So this is 2. You have 2h bar. So you shift up by 2 unit of the ball magneton shift, because this is a classical angular momentum. Okay, not spin. And then this is due to 2 units. But of course, you have some additional shift due to the spin, because this is spin up. So, but it's 1/2. But you have a g factor of 2. So you move by one unit. Is that okay? So you move by 1 more unit. Okay. So you move due to spin, due to shift by spin. So the g factor equal to 2. So you will shift by 1 unit. I don't know how to represent it right. Okay, by 1 unit. Okay, 2 units. So you shift up by 2. Okay, so but this one has 0 angular momentum. So you just shift up. Okay, it just shift up due to the spin. So it will be 1. This will be 1 due to the spin. Okay, but this one, this dark state will shift down. Will shift down by 1. So the g factor plays a role here, because it's spin 1/2, but you need to times the g factor of 2, so it will shift down by 1. Okay, so you can, so how's the band gap? So the band gap decreases. Yeah. Decreases by 4. Okay, you get it? You have a 2 due to m equal to 2. You have 1 due to the spin with the g factor 2. This go down. Then you go down 1. So the band gap decreases by 4. So everything happen here will be reversed in the other valley, because they're connected by time reversal symmetry. So here the band gap increases by 4. So this here we just you go down by 2, you go down by another 1, and then here you go up by 1, and then here you go down by 1. Okay, you go down by 1. So this one will increases by 4. Okay. So what is the g factor for the exciton? So we define the exciton. Now here the g factor is by let's say this is the band gap of K valley. This is the band gap of I should say this, the energy of the dark exciton. This is dark exciton. Okay, the dark exciton at K valley. And then this is the dark exciton at K prime valley. Okay, so the G factor is you have a, a delta E equal to this minus this. How should I write it? It's the energy of the dk minus the energy of dk prime. So in the experiment, you what you measure is this. You have a B, then you apply, you see a cross line, right? You see a cross. Okay, it is this energy gap. Okay, that is the gap that you measure experiment, and that is the d exciton in one valley minus the other one. Okay, so you see a shift, and then that is the G factor of the ball magneton times the B. So that is the G factor of the exciton. So in case you can already see, G equal to 8 for the dark exciton. For the dark exciton. In monolayer WSE2. Okay, you get it. That's how we predict is 8. So what about the bright one? The bright one is you can see that the spin cancel each other. You can see this spin. Let me see this here. The spin cancel each other because this shift up, this also shift up. So it cancel each other. So overall, the D for A exciton decreases by 2. So here is this one. Let me see, this one to here. So this energy. So the energy of A exciton increases by 2. Okay. So the G factor, so the delta E, so delta E for A will be A K prime minus AK. Then it will be G mu B times B. Then G equal to 4 for the bright A exciton. Okay, so here when you say G factor, you have to define. If you only use 1, then the G factor is 1/2 because it only shifts by 1. So the definition of G factor for exciton and for the electron is somewhat different. For electron, it's just the energy shift, but for exciton, it's this shift and combined with that shift. They shift oppositely, so you have twice the difference. So when you read the paper, you need to check the definition whether it's using this or that. But usually for bright exciton, I mean our convention is use 4 or negative 4. People use negative. It depends on which value, minus which value. Okay, so we use 4 negative 4 or 8 or negative 8, and this is a signature of the dark exciton. Like you want to prove it is the dark exciton, then you use this. Can we do it? Can we let me just quickly go to Erfu's paper. We can have a brief look at the data. This paper, okay. So this is our first PIL paper. One of the main results in this paper is the measurement of the G factor for the dark exciton. We show that it is 8. Why is so slow? Oh, okay. Okay, so in this paper, we want to prove that this is a dark exciton and dark trion. Actually, people already proved the dark exciton at that time. This paper we're proving the dark trion. But when you couple to one more carrier, the G factor is the same because the combination is a still excitonic combination. It's just the energy is affected by the Fermi C. But that combination part is still the exciton component. So the G factor is only minorly modified. Okay, so the data is this. This is the data. So you can see that you apply a B field, the value here becomes smaller, the other value becomes bigger. So you measure the emission from here, the emission from here. And we cannot distinguish them. We just measure both of them because they have different energy. So in the data, you just see a cross. Okay, in the data, you see a cross. Then you get the energy difference. You get the energy difference. And these are the energy difference of the dark exciton, the dark trion. Then you plot them, the energy difference as a function of B field. You get the slope. So here we get actually negative 9.5. The reason is because the model that I use here is the single particle very simple model. So in reality, you have other factors that can somewhat modify the G factor, but we get it close. So the bright exciton is this one. This you only see one value at a time because here we use that we detect different circular polarization. So on one polarization you see the A exciton on one value. On another one you see the A exciton on let me see. Okay, here it's only on one part. We only use one polarization. So you see this shift, and then if you flip the polarization, you are going to see another pair. You take the difference, and then you get the G factor is about -4. Okay, so you have -4 here. That is bright exciton, bright trion. They're close to -4. So this one is closer to the prediction here because it's just an exciton. But here, this exciton are interacting. Maybe this one is not interacting with Fermi C. But anyway, for the dark one, it's somewhat more complicated. But you get the value that is still like not too bad compared to our simple estimation because we estimate is 8. So that is actually a convincing evidence that these are the dark states. Okay, so you have any questions? You have any questions? So here we today's lecture we just learn the Dirac equation and take the non-relativistic limit to the 1/c order. Then we get the Zeeman shift and the G factor of 2, and that G factor of 2 actually contribute to the G factor of the dark exciton. Okay, any questions? Zhaoran, you have any questions? Is still here?
No.
Oh. What do you see? Oh, is it another person here? Okay, anyway. So if no question, then we end the lecture here. Thank you very much.